Yeah, thank you for showing up. I'm very glad to tell you something about joint work with Casper, who's sitting in the back there, and Arjen, Ilko, and Peter about intrinsically typed definitional interpreters a la carte. And we'll start with a little quote that you might know by Robin Milner. Well-typed programs can't go wrong. And this is about a very key property in formal programming language definitions, namely type soundness, which captures the idea that if the type checker says okay, then this actually means something in the sense that certain undesirable behavior won't happen at runtime. And ideally, we make this property formal if we define a programming language. But the problem here is that formal verification is extremely expensive in terms of man-hours and thinking power needed. And what we explore in this work is how can we make formal verification of type soundness for programming languages cheaper. And for that, we sort of combine two different approaches that can help you in this regard. One of them is reuse of previous verification efforts by supporting component reuse. That means that you sort of, if you're building a programming language, then a big part of it is going to be things that other people have already done at some point, and you would like to build on their efforts, and that would sort of free up some space to think about the interesting stuff. And then the second thing is that we would like to improve the development experience of type-safe programming languages by using intrinsically typed interpreters. And so what we really do in this work is we develop a notion of intrinsically typed language fragments, which capture the idea of a composable, safe by construction programming language fragment, which can be combined with other programming language fragments to make bigger languages. And what's very crucial here is that composing these intrinsically typed programming language fragments is safety preserving. So that really means that if you have a language that's built out of smaller components, then the type safety property of this language is compositional in the sense that it arises from type safety of the smaller components, and you don't have to redo a type safety proof after composing. So to dive a little bit deeper into these contributions, we first have to spend a little bit of time on this specific style of specifications, intrinsically typed interpreters. So one way you can specify a programming language is by just writing an interpreter. This is a technique we call definitional interpreters. And what you really do there is you write a function like this, eval, which maps expressions to some kind of value. And if somebody comes along and asks you what is the semantics of your programming language, you just point to this function. It's like, yeah, whatever the host language says if you run this interpreter. So this is a small example of a language that has both natural numbers and booleans. And well, let's look at what the interpreter could look like. So for example, if we have addition expressions you see here, to evaluate additions, we evaluate both subterms. And then we have to inspect what is the result of this evaluation. And because this is a language with more than one type, we actually have to look into the value and see is it a natural number or a Boolean? And if it's not a natural number, then we have to return nothing. And similarly, for if and else expressions where we need to inspect the condition, we also need to look into the result of evaluating the first subterm and see if it's a Boolean. And if not, we return nothing. This is a little bit verbose because what we are really doing here is we are writing an interpreter, but because the input expressions are untyped, while there are multiple types in the language, we are in a very subtle way encoding the typing invariant of this language in our interpreter. which means that if we want to prove type safety about this definitional interpreter, we have to redefine our typing invariant and write a proof about that. So in general, this is, tends to be a little bit noisy, specifically because we have this tagging of the different kinds of values that we can evaluate to. And this is something that intrinsically typed interpreters attempt to address by internalizing this typing invariant into the definitions of our terms and into our interpreter. And that means that we have to define 4 things. You define a set of types, which are the object language types, and a mapping from these types to set the values. And a crucial difference here is that where previously these values was a data type where we tagged the different kinds of values with different constructors, here we actually have a mapping from type to set, and we'll see later why that's important. And then furthermore, you define a set of terms, which is now also indexed by a type, meaning that it's not some untyped blob, but instead, if you have a term, you know that it is well typed by construction. And then the definitional interpreter that we use maps expressions of a certain type to values of the same type. And if you have a collection of these 4 things, we can regard it as a safe by construction definition of a programming language. So let's look at an example. So same language, we have natural numbers and booleans, but now we write a function instead of having a data type. And crucially, to stress it again, no tagging to distinguish the different kinds of values. And then the expressions and corresponding interpreter also look very different. And the interesting part is the interpreter here, because now, because the type of this interpreter reflects that we map well-typed expressions to values of the same type, we can just sort of throw away all the error handling that was previously necessary. We can just write, I think, what a human would want to write when specifying this language. And furthermore, ACDA is a total programming language, so the fact that we can inhabit this type of eval, which maps well-typed expressions to a value of the same type, is by itself also a constructive proof that every well-typed expression can be evaluated to a value of the same type in a finite amount of time. So what you're looking at is a type-safe specification of this little expressing language. And what this work is all about is how can we achieve component reuse for this style of specifications, where we maintain sort of the nice, concise nature of these interpreters while still allowing them sort of to be composed into bigger programming language. And that brings us to a little thought experiment. So what we would like is to take these kinds of interpreters and factor them into smaller components and compose them in a way that we don't break the type safety invariant that's encoded in their definition. So what might this look like for the interpreter that we saw just now? Well, so we might want to factor this into if and else expressions and addition expressions, and that means that we're going to have one fragment that defines the Boolean type and its mapping, and another fragment that defines the natural number type and its mapping. And crucially, which is indicated by the yellow bits here, is that these are incomplete definitions. So we define the types and values of these fragments, but we are keeping in mind that at a later point, we, being the fragment, we might be composed with other fragments, and that might bring in new stuff, new types and values that we didn't know about before. And in the same way, we also define the expressions and interpreters in a way, again indicated by these little yellow bits, that we define, well-typed expressions and their interpretation for what we know about, but in the future, we might be composed with other fragments, and then there might be more, and we need to be ready for that. And for these two informally defined language fragments, it's clear that they can be combined, because if you just copy-paste everything together, you'll get the interpreter that we saw earlier. But if we want to do this formally, then a very crucial question is, for any combination of the fragments, are we guaranteed that we'll be able to find a combination or a composition of these fragments that's safe and sensible? So here, just as a quick reminder, this is sort of the fragment that you would get if you would compose the previous two fragments. I've left out the expression data type. And now, suppose someone comes along and says, I also have a fragment which also has booleans, but my booleans are nullable. And I've defined negation for these booleans. Then the question is, what should we do here? Because it's not so clear how these things combine. And specifically, the problem here is expressions of the form if then else, and then the condition being a negation. And there's really two choices we can make here with regards to how we combine the values, because that's really the problem, right? We have two different mappings for the Boolean type. One says bool, the other says maybe bool. We could regard those Boolean types as two entirely different types. And then we have a language with a net type, a bool type, and another bool type. Then this expression would be ill-typed, which is unlikely to be the thing that we want. The alternative is that we identify these two Boolean types. We say they're the same. And then the question is, what do Booleans evaluate to, right? Because eval3 is going to evaluate this negation expression to either a Boolean or null, and then if then else is only going to be able to continue if it's not null. So yeah, no type-safe specification to be gained here from these components. So this is really the crux of composing these intrinsically typed language fragments, is that what we call the canonical forms. So the knowledge that a particular type is associated with a particular set of values, this must be preserved under composition. Otherwise, there is no way that you can be sure that you don't run into the problem we saw just before, right? So can we characterize what it means to preserve these canonical forms in terms of these informal extension points that we've been using? Well, it means that if you try to compose this, in this case it's the 1-2 fragment. If you try to compose this with another fragment, then there are certain constraints that we should impose on the value mappings of the other fragments, namely that every clause of the value type there should either be something that already occurs in our own value mapping, or it should be something that has a right-hand side that we don't know about, right? So another way of phrasing this is to say that if for the types that overlap, you have to agree on what the canonical forms of those types are. Otherwise, you cannot guarantee that the composition of these two fragments is something that's safe. So let's try to make this a little bit more formal. So how would we define these language fragments with extension points in ACDA? Well, the trick is to define them in a way that you assume that there will be more types and more canonical forms from the get-go, but in a way that you, sort of the new types and canonical forms that will be added in the future are compatible with what you already know. So the first thing we should do, and this is sort of a prerequisite, is define the set of terms in our language in a way that we account for the possibility that, yeah, we define a particular set of types, but in the future we might be composed with other language fragments, and they might add more types. So we don't define our set of well-typed terms on type in this case, but whoever uses this thing can pick the set of type, but they have to make sure that, yeah, natural numbers and booleans have to be in there, but it might be more, whatever you need. And then we can, yeah, this all looks very similar to sort of the closed thing with a fixed set of types. But more interestingly, the question is, what do we do in the case of the interpreter? Because that also needs to be defined on a set of values that not we, but whoever uses this thing gets to pick. And here we see the same pattern. We know about natural numbers and booleans, and we say we have a particular mapping for these types, but the interpreter that we define works for any possible value type, so long as you at least include this particular set of canonical forms. And the interpreter actually looks almost the same as before, but what's important here is that we have this up and down arrow, which are casting functions that witness that this v, which includes whatever is on top there, is an extension of value in a way that preserves the canonical forms that we know about. And especially interesting in that regard is the down arrow, because that says that if the bigger value type has an index that we know about, right, t, which is sort of part of the smaller thing, then we can convert it to something we know. And that's, we make crucial knowledge of that, for example, in the if and else branch here, because we use this down arrow to downcast the result of evaluating x. And because we have this witness that value is included in v, we know that this downcast results into something that we know how to handle, namely a boolean. So let's make this a little bit more formal. So what we do is we factor these intrinsically typed language definitions, which consists of 4 things, right? Types, values, expressions, and interpreters. We factor them in 2 entities. The first thing is what we call the canon, which contains the set of types of our language and a mapping of those types to set. And these are the things we care about when composing fragments, because this is what we need to look at to make sure that the composition of 2 fragments is something type safe. And then fragments are indexed or functions over these canonical forms that say, if I have a fragment with canonical forms C1, then actually what I have is an expression type that's indexed by the types in some other set of canonical forms C2, which is bigger than C1, and I have some kind of index preserving function that maps into the values of this set of canonical forms C2, which is bigger than the things that I know about. This is exactly the types of the definition we saw earlier, but just factored in a slightly different way. And what this allows us to do is to write fragment composition in a very nice and concise way. So naively, what we might try to do is write this function. But yeah, there's a hole there, and the question is, what are the canonical forms of the resulting fragment? And that's not so clear, because this entirely depends on what the programmer who is composing this language, how they want to overlap the types, right? Which types do they want to identify? Which types are the same? That's not something that's so easy to compute if these types is just arbitrary set in ACDA. So what we really need here is for the composer to give us a little bit of extra information, which we capture using this ternary relation. And if you have a witness C1.C2 squiggly squiggly C, that means that C is a valid composition of C1 and C2, meaning that, or a consequence of that would be that both C1 and C2 are smaller than C, but in a way that both the canonical forms that C1 defines and that C2 defines are preserved in this bigger thing that we say will be the canonical forms of the bigger language. So yeah, another way of seeing this is that we have two canonical forms, and they might, for some types, some of the types are different in those canonical forms, but there might also be a little bit of overlap in these canonical forms. And in the overlap, the two things that you combine have to agree. Otherwise, you run into this problem that it's not clear that the resulting interpreter sort of maintains the type safety invariant. And then, yeah, this is it. This is the function we can write. You can compose any two fragments so long you can give a witness that the canonical forms can be combined in a safe way. And that's really all you need to do to combine two of these type-safe language specifications in a new one. What else is in the paper? I completely skipped over how do you actually compose these expressions and these interpreters. That's in the paper. You have to do some work, and you use sort of the standard techniques using algebras and faults to do that. Details are not so interesting, but it's there if you want to. What we also do is, so the language fragments that we've been considering so far are actually very sort of simple expression languages with just, it's not much going on there. It turns out that the same ideas can be applied to more interesting languages with some effects, like name binding or exceptions, recursion, or even polymorphic references. So yeah, this is a little picture that's also in the paper. We developed sort of a small library of these fragments to make a case that indeed it demonstrates that reuse is indeed possible. So there's a bunch of languages there, including something mini-ML-like that includes some effects. And yeah, these are all sort of built from the same set of language fragments. And if you want to build mini-ML, this is what it looks like. This is in the artifact. This is part of a bigger module that really doesn't do anything apart from importing the stuff that you want to compose. So I think that's pretty cool. So yeah, finally, to conclude, what do we want to do in the future? I think something that's glaringly missing, at least from a PL person's perspective, is that we don't know how to do parametric polymorphism yet. That's because I think it's not really known how to do that in an intrinsically typed way in the first place. There's some work in that direction, but unclear, if it's possible to do intrinsically typed, and if so, how compatible it is with our approach. And something else is that some of the effects that you may want to model may require or may impose different constraints on what the shape of your semantics. And one thing to think about there is, for example, if you're tracking exceptions, then if you want to do this intrinsically typed, you're going to add some index. Or another thing is these polymorphic references. They also add an index somewhere that tracks the shape of the heap. And currently, how things work is that beforehand you pick you sort of choose your flavor of semantics, which indices am I going to track, what do my typing judgments like, you pick that, and then you can apply these techniques to compose languages that have that flavor of semantics. But what if you want to compose languages that need different flavors of semantics? That's at this point still something we want to look into in the future. So finally, to conclude, what we did in this work is develop intrinsically typed language fragments that allow you to achieve component reuse for the intrinsic style of specification. And yeah, what's I think really nice is that actually making things extensible doesn't really impose that much overhead. There's some encoding going on because we are embedding everything into Agda's type theory. But really, they are similarly concise when compared to the sort of plain specifications that are not extensible, which I think is a nice result. So yeah, that's it from my side. Thanks.
Questions?
So I'm curious how your canonical forms for function types, what they look like, because I mean, the canonical form of a function would, I guess, would depend on the expressions in the composed language, right? Or can you shed some light on that? Or?
Yeah, it would if you would evaluate functions to closures. That doesn't really work well in this setting because then what you get is a non-compositional interpreter that you cannot express as a fault. What works well in many settings is just to reuse Agda's function type, and then you get a compositional mapping. Yeah, which is what we do for many of the examples.
Other questions? Nice work. So if I understood correctly, your ASTs are safe by construction, right?
Well-typed by construction.
Well-typed by construction. Yeah. So how do you handle programs that are not well-typed by the user?
I guess by starting from a point where we assume that a type checker has already run, right? So there's indeed a whole front end that would come before the point where this applies, right? Where you transform some kind of text file into intrinsically typed syntax, and that's we decided out of scope for now. But
do you see a way you can extract maybe a type checker out of the specification?
Not immediately. I mean, probably for the very simple expression types that we looked at now, that's perfectly possible. But in general, that might be, I don't know. I should talk to the statics folks about that.
Thank you.
Other questions?
Yeah, thank you. I was wondering, can you give some intuition about the fragment composition operator? Is it just collecting the proofs of the two inclusion relations, or is there more to it?
Let's see. So yeah, you give the witness of this guy. This ternary relation implies inclusion. So C1 is included in C, and C2 is included in C. So fragment composition gets one of these witnesses, and from that it can sort of get these inclusion proofs. And the inclusion relation is transitive, so it sort of allows you to, then you have everything falls into place.
Just, okay, and that's all that's behind that. Just the two inclusions.
Yeah, just you construct the right witnesses, and then you compose the the two fragments that now have the same set of canonical forms. And I've skipped over this, but yeah, that's sort of the standard data types a la carte tricks that you use there. And that's, yeah, not very, very deep.
Yeah, nice talk, by the way. So in your example of mini-ML, you had one case where the composition of the two C's, I don't remember the term, is not trivial, right? So the copy. I know there's two cases where you have this copy thing, right? Can you explain what that means?
Yeah. So in theory, you can compose these things in any order you want. Here, we've been clever and picked an order where either the canonical forms are equal, and then you use the copy thing, or they are completely disjoint, and then you use the disjoint thing, right? So there's either 100% overlap or no overlap. That's because then these witnesses are, sort of trivial. But you could do it in any order you want, but then you need to construct a witness that explains how the canonical forms combine.
Right, but so here it doesn't look like you have very complicated composition of these sort of these compositions of canonical forms, right? So is that standard? Or because you emphasize that this is very important in the approach, and then at the same time your example shows sort of relatively simple compositions. So can you elaborate on that, or?
Yeah, so I think the thing is we are lacking a good DSL for constructing these composition witnesses, or these witnesses that the canonical forms combine in a sensible way. It's the underlying proof structure in ACTA is a little bit elaborate because there's also some inverse laws that you want to adhere to, and that's just it's a pain if you want to do something that's not this. But yeah, you could imagine that it should be as simple as picking which types overlap and then giving a probably trivial witness that they map to the equal things, and then sort of construct the witness from there. That's not something we've looked at for this work.
Okay, so let's thank the speaker again.